So, welcome to part 3 of the lecture on runtime environments. In the last part of this lecture, we learnt about various parameter passing methods, storage allocation, activation records, static scope, dynamic scope, passing functions as parameters and so on. Today, we will discuss heap memory management and also garbage collection. So, what is heap memory management? What is a heap? To be, we must describe what is a heap. So, if you look at the very systematic allocation and deallocation of activation records, it is clear that we can use a regular stack as far as activation record allocation and deallocation is concerned. But if you consider dynamic data structures such as linked lists and trees, the nodes of such lists and trees are created arbitrarily all over the program possibly, and they are also deleted all over the program. It is not the allocation deallocation is not as systematic as in the case of activation records. Therefore, we require a slightly different mechanism, the dynamic memory allocation deallocation to perform dynamic memory allocation and deallocation in the case of a heap. So, in C programs we have malloc and free to perform allocation and deallocation. The equivalents in C++ programs are new and delete, and finally, in Java programs there is only allocation which is going to happen using the new call. There is no deallocation by the programmer. It is actually done automatically by the Java runtime system. What happens is that when the program runs out of the heap memory, a call to the garbage collector is made. The garbage collector collects all the memory area which is not in use and then returns to the program and continues with the allocation. So, that is how this allocation deallocation happen in various programming languages. So, a memory manager is the one which manages heap memory. So, it implements the allocation deallocation policies, possibly a manual or possibly automatic. So, of course, the goals of a good memory manager are many. First of all, space efficiency. So, as we will see soon, whenever there is allocation followed by deallocation at random, the memory available, the heap memory available gets fragmented. So, the problem with fragmentation is that you may have enough memory available in small chunks, but a very large chunk request for a very large chunk of memory cannot be satisfied. So, this is fragmentation, and we need to minimize fragmentation, so that we can satisfy as many requests for allocation as possible. Then the efficiency of the program itself. So, we must actually take advantage of the locality of objects in the memory and make the program faster. So, how do we do this? If you are able to take care of take advantage of the locality of objects, then possibly the cache will accommodate many objects which are going to be used very frequently, and when objects are located in cache, obviously the programs run faster. The memory manager must also have low overhead. So, allocation and deallocation by themselves should not take too much time, they must take as little time as possible. The heap also needs a data structure for its maintenance. So, usually it is maintained as a doubly linked list or as bins of free memory chunks. So, these two are going to be discussed in some detail in the coming slides. So, what is allocation and what is deallocation? So, let us look at a picture along with this slide in order to understand it. So, in the beginning the heap is one large and contiguous block of memory. So, and then as allocation requests are satisfied, parts of this large piece of memory are cut off from this block and given to the program. So, these are based on the allocation requests of the program. And then possibly some nodes are deleted in the data structures. So, deallocations are performed by the program. Then chunks are these chunks which are deallocated are returned to the heap, and now they can be allocated again. Such free chunks are called as holes. After a number of such allocations and deallocations, memory gets fragmented and it is not contiguous anymore. So, allocation now let us look at a picture to understand what is happening. So, here is a large piece of memory. To begin with, the whole heap is a single chunk of size 500k bytes. So, let us say we allocated all these. To begin with, we made a request for 100, then 50, then 20, then 50, then 200, then 30, then 50 and so on. Then somewhere in the middle of these allocations, we also freed this particular chunk of memory 50k, and then we feed another 50k, finally, we feed one more 50k. It is just coincidence that these are all equal in size, they could have been even the 200k or the 20k nodes. So, once a sequence of such allocations and deallocations happens in any particular order, the memory looks as shown here. So, these are the free holes, right. So, these are the only ones which can be allocated to the program when there is a request. So, for example, if there is a request for 50k block, this can be released or this can be released or this can be released. But if it is for less than 50k, then we can cut off a part of this free memory and return it. But if the request is for more than 50k, say 70 or 100k, or even more than 100k, say 110 or 120 etcetera, even though the total size of the free memory is 50 plus 50 plus 50 150, none of these requests can be satisfied. It is not possible to combine these two into a single piece of memory and then return that contiguous piece as what is required by the program. So, let us go back. So, allocation from a fragmented heap may be made in either a first fit manner or a best fit or the best fit manner. We will see what these are. After a deallocation, we try to combine or coalesce contiguous holes and they make a bigger hole. So, this is needed to minimize the fragmentation, that is what I was about to I was explaining a few minutes ago. So, if possible, if we could really shift this free chunk to this place, and then the busy chunk to this place, and then maybe combine the two free chunks, we get a much bigger chunk. So, these are possibilities, not that every memory manager does all this. So, what is first fit and what is best fit? The first fit strategy, it always picks the first available chunk that satisfies the allocation request. So, there may be many chunks which satisfy the request. As I told you, it is maintained as a doubly linked list. The free chunks are all maintained as a doubly linked list. So, any one of these which actually satisfy the programmer's request can be picked and then returned to the program. So, in the case of first fit, the first one which satisfies the request is taken and returned to the program. Of course, the whole chunk, if it is much greater than what the program requires, is not returned. Part of it which satisfies the program's request is cut off, chopped off from the free memory block and then returned. The rest remains in the doubly linked list pool. In the case of best fit strategy, the allocator searches through the doubly linked list of the free blocks, picks the smallest, which is the best possible chunk that satisfies the allocation request. So, in such a case, if that even if that smallest chunk is bigger than what we require, only a small part will be left out in the heap because of this chopping process. Whereas, in the first fit case, in case it is much bigger, even if the first one is much bigger than what we require, then a large piece has to be cut off and the remaining large piece remains in the heap. So, this may actually increase the fragmentation. So, rest of the chunk remains in the heap itself. So, as I explained, the best fit strategy has been shown to reduce fragmentation in practice, that is the best. It is much better than the first fit strategy. So, because first fit strategy cuts off chunks from the free memory in some arbitrary manner and not like the best fit strategy. There is these two, first fit and best fit, are really very well known strategies. A slightly less known strategy is the next fit strategy. So, what is it? So, the next fit strategy tries to allocate the object in the chunk that has last been split. So, in other words, suppose there is a free chunk x which was actually very large. So, the allocator chopped off one part of it and returned it to the program at this instant. The next allocation is also made from the same chunk. So, whatever was chopped and returned to the pool, the remaining one that stays in the heap, that is used for allocating the next request as well. So, if this happens, it obviously improves the speed of allocation. Why? We already the pointer in the doubly linked list, one of the pointers will be pointing to the last allocated or chopped off chunk. So, if the next request is automatically done from that particular chunk, it is the speed of allocation is good. So, allocation is done immediately, there is no need to search anything. Searching will be definitely required if that chunk does not satisfy our request, then you have to find a different chunk. If it satisfies the request, then the same chunk is used. It tends to improve the spatial locality also, since objects allocated about the same time tend to have similar reference patterns and lifetime as well. So, the result of this is these objects get into the cache one after another, and the behavior of the cache may become much better. These are all together. So, they all get into the cache at the same time. So, the program is going to refer to these objects very soon, and therefore, the behavior becomes much better. Then, so that was about first fit and best fit strategy, and that used a doubly linked list based approach for allocation and deallocation. Here is a different strategy called the bin based heap. So, in this case the free space is organized into bins according to their sizes. So, such a memory manager was proposed by Lee. So, therefore, it is called as the Lee memory manager, and that is what is used in the GNU-C compiler, GCC. Many more bins for small sizes exist in such a manager, because there are many more small objects than large objects. So, that is the statistical information. So, small sizes are used many times, whereas large sizes are not used so often. A bin for every multiple of 8 byte chunks from 16 bytes to 512 bytes is used. So, let me show a picture. So, these are the various bins, and these are the chunks which are actually used for allocation. So, here from 2 to 64 we have exact size bins. In other words, the chunks here are all of 16 size, 16 byte size. The next one will have a linked list here, we have not shown any because of lack of space. So, the linked list here will have chunks of size 24 bytes. The third one will have chunks of 32 bytes and so on and so forth. So, up to this 64th bin, which will have chunks of size 512. These are all exact size bins. So, there is no variation in the size of these bins. Okay. They are all of the same size. These are all of size 16, these are all of size 32, etc., etc. Then we have many of these bins which actually have variable size chunks. So, let us see. So, a bin for every multiple of 8 byte chunks from 16 bytes to 512 bytes, that is what I just now explained. Then approximately logarithmically. So, in other words, every bin is of double the previous size. So, that is here. Okay. So, 576, 640 and so on and so forth. So, these are the sizes of the various bins. So, there are chunks of this size, possibly between 512 and 576, between 576 and 640 and so on and so forth. Okay. So, that is how it would be. Within each small size bin, chunks are all of the same size. I mentioned this just now. In others, they are ordered by size. So, here these chunks are all not of the same size, they may be of different sizes, but they are stored in sorted order. Okay. So, between 512 and 576 there are many chunks. So, these are all stored here, between 576 and 640 they are all stored here and so on and so forth. The last chunk in the last bin is called as the wilderness chunk, which gets us a chunk by going to the operating system. What does that mean? For example, here there may be many chunks, right. So, suppose the memory manager wants something which is much bigger than what is available even in the last bin, this particular bin. Then the last chunk of this particular or the node of this particular linked list is called as the wilderness chunk. So, that is not really a chunk, it is actually going to be some kind of a sentinel, and when we reach it there is a call, the memory manager makes a call to the operating system saying that we do not have any more memory. So, please give us more memory. So, then more memory is returned to the memory manager and the operation continues from that point onwards. That is why it is called as a wilderness chunk. So, how does one manage and coalesce free space? So far we saw first fit based strategy, then best fit based strategy and the bin based strategy for allocating and deallocating space, right. So, how is free space managed? Let us see. So, whenever there is reallocation of a chunk of memory, it is necessary that the adjacent free chunks be coalesced. So, if they are coalesced, then fragmentation reduces because the chunk size now increases. The problem with fragmentation is there are many small chunks and we cannot satisfy a big request. So, now if it is possible to combine smaller chunks and make them bigger, that can be done when free chunks are adjacent to each other, then the fragmentation automatically reduces. So, many small chunks together cannot hold one large object. So, in the Lee memory manager, no coalescing in the exact size bins, only in the sorted bins. So, exact size bins have chunks of the same size. So, there cannot be any coalescing performed on those bins, but in the other bins that we saw, there are chunks of various sizes. So, it is possible to coalesce them. Only thing is, when you coalesce and they become much bigger, they may have to be shifted to a different bin altogether. Then how is this coalescing done? We use what are known as boundary tags. So, this is a bit which indicates whether the chunk is used or it is free, and there is also information about the chunk size itself. So, this is maintained at the end of each chunk for both used and free chunks, and there is a doubly linked list of free chunks. This is true for first fit best fit strategy and also for the bin based strategy. So, let us look at a picture. So, we have 3 chunks here, all the 3 chunks are adjacent, C is occupied. Okay. So, it is really being used by the program. Chunk B has just been deallocated, A was deallocated quite some time ago. So, this was returned to the free list, okay, or the heap. So, now because A and B are adjacent, they can be merged, and we can create a single node of double this size. So, how can this be done? So, let us look at the boundary tags first. So, 0 here, 0 here at the 2 ends of chunk A indicate that the chunk is free. Similarly, 200 here and 200 here at the end of chunk A indicate the size of this free chunk. The same is true for chunk B. Observe that this boundary tag and this boundary tag are 0, indicating that both are free, but this chunk is free. Whereas, for chunk C, which is occupied, the boundary tag is 1. The size information is maintained and the boundary tag information is maintained for all free and also occupied chunks. So, when this particular chunk B is freed, it is easy to see that the adjacent bit, the boundary tag bit, free used bit can be checked, right. So, it is one location beside this in memory. So, if that is a 0, then we know that this entire chunk is free. So, when it checks the chunk on the right side, it is a 1. So, therefore, this entire chunk is not free. So, you cannot really coalesce B and C, you can only coalesce A and B. When we coalesce A and B, these 2 links have no meaning anymore. It is only this link and this link which matter to us, right. So, we manipulate only these 2 links and we forget about these 2 links. The size, this boundary remains as 0, the size information becomes 100 plus 200 plus 100, 300. In this here becomes 300 and here also it becomes 300. So, that is how chunk coalescence happens. The merged chunk KB may have to be placed in a different bin if it is a bin based memory manager. What are the problems with manual deallocation? For example, there may be memory leaks, failing to delete data that cannot be referenced. So, we have actually started manipulating links in a linked list. Maybe we made a small mistake in the program. A link point which was pointing to the next node now points to some other node, right. So, the node which was being pointed to now is not reachable anymore, it cannot be referenced at all, but the programmer forgot to delete that particular node. So, this is failing to delete data that cannot be referenced anymore. So, the memory is being used, it has not been returned to the pool, the heap. So, we do not have memory to that memory cannot be used for allocation, okay, but it is a waste. So, this is a memory leak, and such memory leaks are very important in long running or non-stop programs such as monitors and operating system programs, because it is not as if the program stops, the memory gets flushed and all the objects go away and we start all over again. The memory which is wasted in this manner will actually be wasted forever, there is nothing we can do about it. So, memory leaks are very important in such long running or non-stop programs. Then we have the famous dangling pointer dereferencing. So, here we are referencing deleted data. So, this is very common. You think that the link is not null, you try to actually do some a dot or a pointer data and so on and so forth. Unfortunately, A is null, there was a problem with the program, it was not written well. So, A is null and you are trying to access null dot something, no, not possible at all. So, this is a dangling pointer dereferencing problem. It happens because of programmers bugs. So, both these are very serious and very hard to debug. Therefore, if we can actually do allocation automatically, then some of these problems may be eliminated. So, reclamation of chunks of storage holding objects, storage holding objects that cannot that can no longer be accessed by a program is called garbage collection. So, GC should be able to determine types of the objects. So, we will know why, okay, very soon we will know that. Then the size and pointer fields of objects can be determined by the garbage collector. So, once I know the type of the object, I know the size of the object as well. This is the point. So, languages in which objects can be determined, types of objects can be determined at compile time are known as type safe. So, even if they can be done at runtime, even then they are called type safe. So, it is even stronger if it can be done at compile time. Okay. Java is type safe. You can determine the types of objects at most of the time you can determine them at compile time. C and C++ are not type safe. Why? Because they permit type casting. So, you can convert any type to any other type in C and C++. So, which creates new pointers. Thus, any memory location that can be theoretically accessed, that can be accessed theoretically at any time, and hence it cannot be considered as inaccessible. So, you have a problem here. You typecast one variable to another type and then you try accessing it. So, in other words, you can make anything a pointer anytime, try accessing any part of the memory. Well, you may actually get a core dump and the program may stop, but that is beside the point. How is garbage collection performed? So, the concept of reachability of objects is very important here. See, there is something called a root set. So, the root set is all the data that can be accessed or reached directly by a program without having to dereference any pointer. In other words, most of the time these are the variables which are declared by the programmer. Okay. So, of course, there are slightly other possibilities, but most of these elements, most of the elements of the root set are programmer defined variables, okay, pointer variables. Then we determine this root set to begin with. So, look at they are all pointers, right. So, recursively any object whose reference is stored in a field of a member of the root set is also reachable. So, these are first level are programmer defined variables, they are definitely accessed by the program. So, they are reachable. Now, you look at the inside of this particular object which is pointed to by one of the members, field members of the root set, right. So, that is also reachable. So, many pointers as fields. So, each of these can be the objects can be accessed from these pointers, they are all reachable. So, this goes on recursively, in other words it is like a graph, right. So, from the root set you have many other. So, imagine a tree, right. So, you start with the root which is pointed to by a programmer defined variable, then slowly gradually if the root the left link and right link can be traversed, then they become reachable, then the left link and right link of the children can be traversed and so on and so forth. So, recursively the whole tree becomes reachable. Now, new objects are introduced through program allocations, object allocations, and they are added to the set of reachable objects. So, how we do this we will see very soon. Parameter passing and assignments can propagate the reachability of these objects. So, new objects are created through new or malloc calls, right, and when we pass some pointer as a parameter to another function, then the objects pointed to by this parameter are visible within that function also. So, then you can manipulate a little more and the reachability propagates there. Assignments and ends of procedures can terminate reachability. So, this is if I have A equal to B, both are pointers, whatever was pointed to by A is now destroyed, now B is copied to A. So, now from now on that variable A points to whatever B points to. So, this assignment has ended the reachability of objects which were reached by A. So, similarly ends of procedures, when I return from a procedure all the local variables are lost. So, the reachability of objects from those local variables is also reduced or affected. Similarly, an object that becomes unreachable can cause more objects to become unreachable. So, I will show you a picture to demonstrate this. So, what does a garbage collector do? A garbage collector periodically finds all unreachable objects by one of the two methods. First method is catch the transitions as reachable objects become unreachable. So, we will see the reference counting method, which is one of these one such method, or periodically locate all reachable objects and infer that all other objects are unreachable. So, this method we are not going to describe. So, there are many such methods under the second category, they are far more complex, and garbage collector itself can become the topic of very serious discussion. So, let us look at the reference counting garbage collector, which is an approximation to the first approach mentioned above. That is, when an object changes its state from a reachable object to an unreachable object, we catch that object and do something. So, let us see what we do. We maintain a count of the references to an object. So, as the program or the mutator performs actions that may change the reachability set, okay. So, this count also is going to be changed. So, when the count becomes 0, the object becomes unreachable, and reference count requires an extra field in the object and is maintained as below. So, here is let me show you a picture to understand reference count manipulation, and then we go back to discussion. So, here is a data structure. There are 4 nodes A, B, C and D. A was pointed to by some programmer defined variable. The programmer did not want this data structure anymore. So, he made the pointer which points to A point elsewhere, so this particular thing became garbage, it is not reachable anymore. But the reference counting fields do not say the same thing. For this, the reference counting field has now become 0, because it is not reachable from any other variable or pointer. This reference count field is 1, because this node is pointing to it. Similarly, the reference count field for this is 1, because this node is pointing to it. The reference count field for D is 2, because both these nodes are pointing to it. But the situation changes very soon. The reference count of this is 0, so it is garbage collected, this disappears. Now, because the node A disappeared, the reference counts of B and C have also been made 0, that happens during the collection process. So, these two will also be now removed by the garbage collector. So, then the reference count field of D also becomes 0, and that is also collected by the garbage collector. So, let us go back and see how the reference counts are maintained. If there is a new object allocation, then reference count is set as 1 for the new object. So, the new object is created. So, there is a pointer pointing to it, and that is what is returned by the malloc or new call. So, it is reasonable to set the reference count 1 for the new object, there is only one pointer pointing to it. parameter passing. So, reference count plus plus for each object passed into a procedure, that is each parameter that comes into the procedure is pointing to some object. Now, because this is a this becomes a variable in a different procedure, we can say that the reference count now becomes one more, because there is a new variable which is pointing to it, that is the parameter itself. Assignments to reference assignments. So, u equal to v is the assignment statement, where u and v are the references. So, reference count plus plus for the object star v, that is this particular object, okay, now is star v, whatever is pointed to by v, that will also be pointed to by u now. Okay. V was pointing to something, now u also points to it. So, now the object star v has one more reference. So, reference count plus plus. For u, it was pointing to something, now from now on it points to what v points to. So, for the object which was pointed to by u, it is reference count minus minus, okay, object star u. Procedure returns. So, for returns, reference count minus minus for each object pointed to by the local variables, this is what I was saying. So, once the procedure returns, all the local variables which are pointing to some objects are not available anymore. So, reachability reduces. So, reference count minus minus for each object pointed to by the local variables. Transitive loss of reachability, this is what I showed just now. Whenever reference count of an object becomes 0, we must also decrement the reference count of each object pointed to by a reference within the object. So, this is what it is. So, these two fields are pointing to this node and this node, the reference count of A has become 0. So, we are going to actually reduce the reference count of this by 1. So, this becomes a 0, this also becomes a 0, and finally, this is pointing to this is pointing to this, both of them decrement this reference count by 1. So, this also becomes a 0, that is what I showed just now. Finally, D is also collected. What are the advantages and disadvantages of the reference counting type of garbage collector? The red ones are all disadvantages and the blue ones are all advantages. There is a very high overhead due to reference maintenance. For every assignment statement involving pointers, you do a plus plus or minus minus, etc., etc. So, there is a lot of overhead due to reference maintenance. You have to keep manipulating the reference counter, and you cannot collect unreachable cyclic data structures, circularly linked lists. I will show you an example of this, since the reference counts never become 0. So, the same old picture, this pointing to this pointing to this pointing to this, right, but I have also added a cyclic part here. So, this points to this and this points to this, right. So, this counter is still 1, because this is the pointer pointing to this, right, this field is pointing to this particular node. This counter is 1, because this field is pointing to this node. This counter is 2, because this is pointing to it and this is also pointing to it, right. So, this is 2, because these two are pointing to it. So, none of the nodes are in the root set, okay, but no programmer defined variable is pointing to any of these, but because of the cyclic nature of this particular data structure, none of these reference counts are 0, and therefore, none of the nodes can be garbage collected. So, this is the problem. What are the advantages? Garbage collection is incremental. Overheads are distributed to the mutator or program's operations and are spread out throughout the lifetime of the mutator. So, if you have run any Java programs and when it runs out of memory, the Java program just pauses. So, you try doing anything, click a mouse or something like that, click a button, nothing works. This is because the Java program is now doing garbage collection. This is the pause that I was talking about. So, in the reference difference counting type of garbage collection, there is no such pause. Overheads of reference counting are distributed. Slowly, gradually the memory becomes unreachable, and as soon as it becomes unreachable, it is returned, that is reference count becomes 0, the memory chunk is returned to the heap. So, it is incremental and it is very fast. Garbage is collected immediately and hence space usage is low. So, imagine you had a large chunk of memory, you went on allocating it and no collection was made. Only when the entire memory was consumed, the garbage collector was ran, garbage collector ran, and then it collected and went back to the program. So, here you probably need much more memory, even though some parts of it became free in the middle, because you are not really collecting such free memory somewhere in the middle. Whereas, with reference counting type of garbage collection, garbage is collected immediately once the reference count becomes 0, and hence you can probably do with less amount of heap memory. Reference counting method is very useful for real time and interactive applications where long and sudden pauses are unacceptable. So, this is what I just now told you. Java programs introduce such pauses, and these may be unacceptable to us. Therefore, this reference counting GC, even with its limitations, has its place in real time and interactive applications. So, that is the end of the lecture on runtime environments. So, now we begin the lecture on local optimizations. So, the outline of the lecture is we study and understand what are basic blocks, what are control flow graphs, some of the local optimizations, how to build a control flow graph, directed acyclic graphs, value numbering and things like that. So, why are all this very important? So, we know that the intermediate code generator produces intermediate code in the form of quadruples or trees and so on. Now, because of the control instructions, jump instructions in the program, the sequence of quadruples can be actually partitioned into smaller blocks and a graph structure can be accorded to them. So, these blocks are called basic blocks and the graph is called as a control flow graph. So, this basic block plus control flow graph structure is very useful in optimizations. So, we will see how they are done, and they are also useful for machine code generation, that will be studied sometime later. So, what are basic blocks? Okay. So, basic blocks are sequences of code with a single entry and a single exit. So, we can so let me give you an example. So, there is only a straight line sequence within such a basic blocks. Okay. So, you cannot quit until you come to the end of the basic block. Take this big block, there is no control jump instruction somewhere in the middle of this particular block, it is only at the end. Okay. So, this type of sequence of quadruples is known as a basic block. So, they have a single entry and a single exit. So, we consider the quadruple version of intermediate code. So, that explanations are easier, but with some modification we can also process tree intermediate code. Flow graphs actually show the control of flow between these basic blocks, and basic blocks are represented as a directed acyclic graph. So, I will show you some examples of this, which are in turn represented using the value numbering method, which is applied on quadruples. So, we are going to study all this information, all these processes along with optimizations on basic blocks. So, this is an example of a control flow graph. So, if you look at the sequence of quadruples alone, we would have prod equal to 0, I equal to 1, then T 1 equal to 4 star I, etcetera, etcetera. Then we have if I less than or equal to 20, go to B 2. Instead of B 2, it would be quadruple number 3. Okay. This is number 1, this is number 2, this is number 3, and so on and so forth. Finally, this will also become number 3, and finally, following that would be the stop. Okay. So, that is this each of these is a basic block, and the control flow is between these basic blocks. What are the local optimizations that we can perform? So, optimizations which are performed within a basic block are called local optimizations. So, we are not going to move any quadruples from the basic block to some other basic block when we perform local optimizations. We move quadruples within the basic block, or we delete quadruples within the basic block, change them within the basic block, but nothing leaves the basic block and goes to some other basic block. So, if it goes to some other basic block and there is code movement across basic blocks, that would be a global optimization, and that will be the subject a little time later. So, local common subexpression elimination is one of the very important optimizations. So, as the name suggests, if there are many expressions A equal to B plus C, x equal to B plus C, etcetera, within the same basic block, P plus C is a common subexpression. There is no need to compute this subexpression again and again under certain conditions, that is B and C are not modified. Then it is also possible to do dead code elimination. What is dead code? Instructions that compute a value that is never used. So, it is possible that we just use another extra variable, assign it a value, and the variable is never used in the program. How does this such a thing happen? It may not be intentional, and it may not be done by the programmer the first time he or she writes a program. When the program is being debugged, when the program is being changed, it is possible that some variables are introduced and some are not used anymore, and the programmer forgets to delete the declaration of such variables or even the assignments of such variables. It is also possible that some code is introduced into the program for debugging purposes, but it does not actually contribute to the program performance alone. Reordering statements that do not depend on one another. So, such reordering may actually increase the speed of the program. For example, if a load can be done early, then the statement some other load can also be initiated at the same time. So, these loads may not depend on each other. So, we may want to move them appropriately, so that some delays are taken care of. Reordering computations using algebraic laws. So, algebraic laws are commutativity and associativity. So, we will see how this can be used later on. For example, to give you a simple example, if B plus C is a expression, C plus B is another expression, if commutativity holds, these two are equivalent. So, we can, if we can detect such computations using commutativity or any other algebraic law, then the code can be improved. So, the above two optimizations can be applied only on directed acyclic graph or tree representation, that is the reordering of statements that do not depend on one another and reordering computations using algebraic laws. So, we will see how to do this using value numbering as well. One of these can be done using value numbering. How do you partition the quadruples into basic blocks? That is the next topic. The algorithm is simple. So, essentially we determine the set of leaders. So, what are leaders? The leaders are the first statements of basic blocks. The first statement in the program, that is a procedure, is a leader. Any statement which is the target of a conditional or unconditional go to is a leader. I will give you an example of this, and any statement which immediately follows a conditional go to is also a leader. So, look at this example. So, we had prod equal to 0, then we have I equal to 0, then we had T 1 equal to 4 star I, etcetera, etcetera. Finally, read this B 2 as 3, number 3, okay, because it is going to 3. So, at this point when we scan this, we find that we I less than or equal to 20 go to 3. So, that means 3 becomes a leader, because it is the target of a conditional go to statement. And this statement, the stop statement immediately following this is also a leader, simply because it is following this conditional go to and it is not after an unconditional go to. So, any statement which immediately follows a conditional go to is also a leader. So, a leader and all statements following it up to but not including the next leader is the basic block corresponding to that leader. So, for example, here. So, we marked this as a leader, we marked this as a leader, we marked this as a leader. So, start scanning from here up to this point, that is these two statements, that is one block. From here, which is a leader, to this point just before that is another basic block, and this stop statement is a basic block on its own. A leader and all statements following it up to the next but not including the next leader is a basic block corresponding to that leader. Any statements not placed in a block can never be executed and may now be removed if necessary, if we want to do that. What is a control flow graph? The nodes of the control flow graph are basic blocks. So, we saw this already. One node is distinguished as the initial node. So, here this is the initial node. There is a directed edge from B 1 to B 2 if B 2 can immediately follow B 1 in some execution sequence. So, how do you determine this? There is a conditional or unconditional jump from the last statement of B 1 to the first statement of B 2 and or. So, let us do this. There is a conditional or unconditional jump from the last statement of B 1 to the first statement of B 2. So, for example, here. So, the last statement of this particular block to the first statement of the same block, it could have been a different block. So, this is the arc, right. So, here is a control flow and this corresponds to an arc. B 2 immediately follows B 1 in the order of the program and B 1 does not end in an unconditional jump statement. So, here. So, this stop statement follows this, right, and this is a conditional jump and not an unconditional jump. So, this is another arc which is added to the program, so to the control flow graph. How do we represent basic blocks? A basic block is represented as a record, and what does the record consist of? A count of the number of quadruples in the block, a pointer to the leader of the block, these are essential, right, pointers to the predecessors of the block. So, this is the representation for the graph structure and pointers to the successors of the block. So, again this is a representation for the graph structure of the program of the control flow graph. So, we need these things when we want to traverse the control flow graph in a particular order. So, we may want to do a depth first search on the control flow graph, or we want to do a DFS on the reverse control flow graph. So, all this become useful at that point. Note that jump statements point to the basic blocks and not quadruples, so as to make code movement easy. So, let us see what happens here. So, as I said, this I less than or equal to 20 is go to is it says B 2 and it does not say 3. Suppose it had said 3 and because of some optimizations not necessarily local, it could have been global also, we moved some of these statements such as T 2 equal to address A minus 4 and T 2 equal to address B minus 4 into block 1. So, these two move here, right. So, then block 1 will have 4 quadruples and T 1 equal to 4 star I will become the 5th quadruple. If we had written I less than or equal to 20 go to 3, it would have been an error. We had to possibly go and modify this as well. So, what we really do is write this as B 2, which implies a pointer to the beginning of the block So, thereby any changes in the block, the movement of quadruples even to the outside will not affect it. So, we always know what is the first quadruple in the block, right, that would be T 1 equal to 4 star I, even if these are moved. Even if T 1 equal to 4 star I is removed from the block, there would be some other quadruple, it does not matter which quadruple is the first, we only want to make sure that this pointer is to the beginning of the quadruple. So, that is what this is saying. So, it makes code movement easy, and then it is not necessary to patch code whenever we move some quadruple outside the basic block. So, we will stop at this point, and in the next part of the lecture we will discuss the directed acyclic graph representation of a basic block and how to perform various optimizations on the basic block. Thank you very much.